Hey, thanks for having me. It's great to speak at this venue. Actually, this is the first time I have been to AUTOML conference, the first time as an author in Baltimore, 2022. And I can still recall that last time I've been to this conference, people are still talking about the neural architecture search, learning rate tuning, and all those things. And it seems that after 3 years, people have an interest shift already, which is interesting. I was discussing with Frank and Roman last night. So when I consider what to talk, I feel perhaps I could offer another perspective of AutoML if it hasn't been discussed yet. Instead of optimizing model architecture as a learning hyperparameter choices, we could have a higher level of automation, automating the workflow, and especially when today the machine learning and AI system has been more and more compounded with dense component being put it in. And if we have workflow and many different things connected together, how efficient optimization of maybe localized part, a small part could tweak and steal the behavior. That's what I can talk today. And I want to show you it actually has many interesting connections with technique we are already well known in the auto differentiator in the AutoML community, such as the well-known auto differentiation. So let's talk about, wait, it's not automated, sorry. Should have been. All right, so let's talk about AI. Well, generative AI, large language models are powerful. We're using that every day, of course. And besides the general ability, what you want the AI to understand you, work for you in a customized role. And unless you are 1.01% of the people who will fine-tune the model or train your own models, what other people, other average people like us would do, we will prompt the model and tell it as much as we can, right? What is a good prompt model? What a good prompt model will look today? Well, here is one of the general pipeline I tend to follow when I write my prompt. I will first define a role. Say, okay, started by saying that you are a very experienced AutoML researcher who will always tell me the truth and no bullshit, absolutely. Say something like that. And then define the task, my problem formulation, and then establish the context. A common way to do that is to give a few examples saying that, okay, so now I want to solve this task A. I have solved a similar task B, C, D before, and those are ideal answers. So let's take reference to those. And all those things plus some other instructions, guide rails put together into a prompt, throw it to GPT and see what answer give you. Maybe you're happy the first round, but more often than not, you're not happy. You will need to reiterate that a few times and you get the best, you get a pretty good result. And given today's generic foundation models, prompting actually already display very sophisticated behavior, meet many daily needs. All right. When GPT and other models first come to play, prompting sounds a pretty, how to say, amateur thing that you just write a few sentences and yeah, doesn't sound like a lot of science. But things have changed quite a bit in the past few years. For example, how many people have heard about the famous cloud prompt leak earlier this year? It's still there. If you're interested, search GitHub. You can still find the leaked system prompt. So people were more or less surprised, not quite so, but still, we actually see it. Grok has Cloud has accumulated how much? 60 pages in PDF of prompt that they were customized the language model behaviors, what do and what should not do. And in token, that's tens of thousands of them. This is just a screenshot of page one. Many and you should and we shouldn't be surprised that now this list now this length has grown even longer. And so with more and more people customizing the LLM's APIs for their own server, for their own daily usage, and also when you deploy those APIs into production, you expect those to get more and more catered to user needs, involving more, personalizing more, so the prompt even need to change over time. That have lead us to one clear conclusion, that is, you cannot expect you hire some engineer to rewrite this long 60-something page prompt for you every day. This won't scale for the business scope opening. What shall we do? The conference title tell us we will automate that, right? It hasn't been long since LLM being invented that people realized that LLM itself could provide a blessing for providing prompt. There are several pioneer work, and I'm citing one of the early ones by Joe and others in 2022 called Large Language Models, Human Level Prompt Engineers, a purple method called Automated Prompt Engineer or APE. The key innovation is for today, pretty straightforward, but for that time, pretty fresh thing. They show that you can use another frozen LLM to provide a prompt for the frozen LLM that you're using. Let's look at how it works. So start from a simple text. Let's say here, sentiment classification of the input. Let's say I'm a beginner to use to write the prompt, and the prompt is instruction. Classify the input as positive, negative, and this is the input. I want to pause here and ask people, how do you think about this prompt? Of course, it's a simple one, but it's a simple task as well. Anyone think this prompt is apparently problematic? It's bad, useless, wouldn't serve your purpose? Anyone find this obvious? Yes, please. Great. You should consider doing a prompt engineer. Right. Exactly. This looks pretty nature for a human to write it, right? Because you kind of assume you already know what you want, but you didn't communicate that very well to language model, and so that happens to us every day. Start from a simple prompt, and let's take the first input, and the LLM will LLM will have a wrong classification negative, and then at this point, we will introduce another LLM, and this second LLM also frozen, same as the first one you're using. Let's assume both are cloud APIs. We'll look at the prompt, the input and output, and we will instruct this LLM to analyze why and provide feedback how you could improve the first prompt. So let's assume this LLM is so smart, like this specific audience, that is able to detect that, okay, you didn't specify what you want to classify, right? Who knows what you're asking for? So instead, after discovering that, this LLM engineer will make a revision to the prompt. Maybe add one sentence. You should pay attention to the sentiment and keep rolling like that. This is a simple case, but in complicated settings, this evolution could go thousands of iterations and take a million data samples to discover the right prompt. So then let's zoom in, look at this black box called LLM engineer. How we do that? Apparently, you will need another LLM to generate a few revision suggestions. But then how do you select? How would you recommend? APE follow a three-stage pipeline, using LLM to generate a candidate, score those candidates based on some evaluation function, and then using Monte Carlo search to probabilistically decide which one we recommend. This is a pretty standard baseline, and may remind you of many things we have done in other hyperparameter optimization. Right? Despite this simplicity, this method already demonstrated that can reduce instruction writing efforts from hours to the automated prompting by minutes. So quite promising. Since that many work has been discovered, it's impossible for me to give a fair overview of all this work. But I do want to highlight one of the popular package coming out of those work called DSPY from Stanford NLP Group, Declarative Self-Improving Language Programs. This was my favorite for a while because that very elegantly modern the process of building a compound AI system into a programming-based programming-like structure. So let's start from training data. The first thing you use DSPY is you write a program to specify which component you want in a pipeline. Just consider you have function blocks. You introduce those modulars as writing functional blocks, and you put those functional blocks together, and you define a validation method, and putting all those together into the backend engine called the DSPY compiler. What this DSPY compiler to do is connect all those things together, make it into a runnable program, and then find out which part of the program need optimization. And this will work then like an optimizer in a differentiable system and enhance those variables. In most of the application of DSPY, those variables are considered to be the prompt because many other things are just LMs or retrievals, others, and not much you can optimize over that. And DSPY has separated the program construction from the prompt optimization. So this part is done by the compiler. This part will be handled by the optimizer, and they will iterate from each other. Very clean to use. And for the optimizer part, how to select the prompt, DSPY has been following the trend starting from APE to natively support the discrete search method. I think almost all the methods they have it discrete. Random grid search, random search, grid search, Bayesian search, combinatorial search. Again, pretty much similar to this community, I guess. Though it should be very resilient of the classical machine learning hyperparameter tuning, but scale and must scale in a more systematic way and very clean interface to use. Okay, so far we have been doing pretty well with the discrete search method. And but now if we take the length to view the prompt as a variable, we must come to notice that we're talking about a pretty high dimensional hyperparameter space, right? We're not talking about searching 1 or 2 learning rate. We're probably talking about searching tens of thousands of tokens, and if you consider each token to be a variable, that's a very high dimensional hyperparameter configuration you have to consider. How to deal with this scalability challenge? Like many other things we run into machine learning, when we cannot search, when we find a search doesn't scale, discrete search facing difficulty of scale, we will go to continuous relaxation and let the gradient help us. That has see another regime in prompt optimization, the continuous way. Again, so many works. Just two representative one, just two early representative one here. For example, in the hard prompt made easy paper in 2023, people they were first project the discrete token into a continuous latent space, optimize over there, then project it back. The another paper, Prodiga, will directly optimize optimize the discrete tokens using pass-through technique, and a later version of that using Gumball softmax technique. All those things should sound familiar if you ever work on NAS, right? Type of thing. And that has definitely helped the scalability and allow us to optimize longer prompt. And from those, but what is more interesting is from those things, and if we see this now, instead of seeing it as a discrete search system, now seeing it as an end-to-end differentiable system, we find it's very similar to other things that we have been using for ever, right? It looks like a backpropagation. All is the mother of backpropagation, auto-differentiation. Right? If you consider machine learning pipeline to be a cascaded structure connecting step 1, step 2, step 3, each has the input-output blocks, each black box, and each black box, you consider them to be a layer in a neural network. They are almost, you are looking at the counterpart of optimizing a multi-layer neural network. The only difference here is the variable you have to optimize now lies as an input of this multi-layer system, which has a prompt. So auto-differentiation is nice because to me, it takes a blended view between symbolic and numeric. It can optimize an arbitrarily complicated function by never directly looking at the whole function. Instead, it looks at the computational graph of the function. That's a key concept. And then dive into the graph, compute partial derivatives at each node of those graphs, and then use back chain rules to chain them back together. So in this way, you can divide and conquer and evaluate really high dimensional functions. Really good stuff. All right. So seeing this connection, there was a very interesting paper last year explicitly point out, hey, there is the connection. That was a paper called Text Grad, Automatic Differentiation by Text. It was a Nature paper from Stanford James's group. This is a very interesting paper because it draws a conceptual connection to my best knowledge for the first time. Maybe not, but I read it first time to realize it the first time. This paper draws a conceptual connection between prompt engineering and auto-differentiation, and did apple-to-apple mapping between concepts between the two with the two. So let's look at so in their system, you will have a backward engine to evaluate how the current prompt lead to the current system performance, good or bad, and that is like a loss function in a neural network. And a frozen LLM will take this evaluation and generate a revision, suggestion, or critique to the variable, in most cases, the input prompt. So if we consider it to be the counterpart of gradient descent, who are the gradient? the gradient as a text revision, suggestion, critique, the second LLM is providing about those variables. Because just like a gradient is about to update weights, those revisions is meant to update the prompt. The update signal is the counterpart of the gradients. And then what are the variables? In neural network, those are the weights of layers, but in this case, it's the input of the prompt if you don't want to touch the blocks. So they made very interesting equivalence. So the prompt revision process is therefore conceptually, loosely equaled as the gradient update process, and you can do that iteratively. That's how they build this conceptual mapping. I do want to make it clear that this text grad is not really using numerical gradient to solve prompt optimization. It's a high-level modeling to build equivalence between the gradient backpropagation and the auto-differentiation of prompt. And later we will see that lead to some pretty easy to understand and use code implementation in PyTouch sense. I would say this is more understanding way to say that rather than the numerical precise way to say that it is not using gradient actually to solve the prompt. So how they actually do, let me show you. Gradient, so on the left of this page is what we're more familiar with, right? The true gradient. You take an input, you go through a hidden layer, you go through a weight layer with all the variables you want to optimize, and you have a hidden layer, you pass through another weight layer, you get an output, and you can evaluate it with the ground truth, generate a loss function, and backpropagate back and update everyone, right? That's a backpropagation C. Now, let's try to move your L spotlight from the left to the right and try to appreciate the system on the right, how it looks resemblant to the left. This is a pretty simple, I will say, LLM workflow. We'll start with a prompt, and this prompt goes through LLM. And this LLM may be triggered to make some query to search some materials to do RAG. So it will have a query to go to the search engine. And it may also trigger the tool use to generate some other intermediate output. And usually the original query output plus the RAG plus RAG materials plus tool use like search result will concatenate together. And I'm not satisfied. I'll put them all together and go through into maybe the same LLM again or another LLM and use this extended scope to do another analysis. And this final analysis, maybe this is a document summarization, maybe it's a deeper reasoning, whatsoever that is. I just want to look at it again, okay, to derive a better answer. So this further refined answer is then need to be evaluated. Different from a neural network case where we do have a ground truth to evaluate. When we generate the answer, we don't have a ground truth. So what does evaluation mean? That is similar to what has been doing since APE time. We will use another frozen LLM and give it some evaluation instruction. This is LLM number 2. We will give this LLM number 2 some evaluation instruction and ask this LLM, how do you think this output is doing the job of what is being asked in a scale 1 to 10, maybe? Give me a rating. And beyond that, I want this LLM to also tell me if I want to improve this rating, for example, how I should write the input prompt, how I should change my way to prompting this LLM. So this LLM is responsible for generating the so-called loss, which is an answer rating, and the so-called gradient in this text grade system. And the gradient here, remember, is not a numerical gradient, is a revision suggestion that you can take into account to update what you have input this way. And this revision suggestion will be sent back following exactly the same philosophy of auto-differentiation. For example, for this step, I would only comment on its intermediate input, how it can improve. And from this step, it's another LLM. After I receive the signal from my upper hand, this response can be improved by, I will take this feedback as my new, together with my old prompt to rerun my task again and generate a new prompt for myself. And this LLM then again could look back into its its predecessors and do what LLM is do this LLM or do what this LLM is doing to itself. I'm doing that to my predecessor. How well you are doing and how you can improve yourself. You do it in a cascaded way back, only locally and eventually until you reach the earliest prompt. That is a LLM equivalent stage of backpropagation, if I'm making some sense. So this work has been implemented in another pretty nice PyTouch package, text grade. And if you're familiar with Python coding, this should look pretty easy to comprehend for you. Similar to in Python, though, you will have input data. Well, if you are, for example, I'm writing an image classification, I have a tensor input, I have to declare backbone, declare loss, and then declare optimizer, what you do in configure file, right? And now, if you want to do this textual gradient, you literally do the same thing. Declare your input, which is your training data you want to afford for tuning your prompt, maybe 50 articles or 100 text reviews. This is a training data declaration. And you declare LLM plus the initial prompt. So this is like the initialization weight for ResNet 50. So I could give it the initial prompt called UR summarizer. You need to define a loss function. In LLM, you have a ground truth and a numerical function. Here, you will give a task specification, rating the summary, how well I'm doing. And the optimizer eventually will propagate the gradient back, but in a highly packaged way in what I just described, and optimize every variable, every prompt that it will meet in the way back. So you can just write about it like you are training a neural network. And they have demonstrated this actually works in not only optimizing NLP task, but also optimizing coding and molecular task. And you're welcome to check their paper. All right. If I haven't made it clear so far, I want to make it clear now. Nothing so far was done by me. So why I'm shamelessly talking about those stuff? Because I want to start my own critic process. Those things are great, but what haven't been addressed yet? A few things that caught our attention when we started working on this in this domain. Most SOTA methods first are designed for a LLM pipeline, but they often adopt a simpler conception of pipeline, one LLM or multiple LLMs in a cascade. However, if you look at the more recent LLM applications, you will often see more than linear workflow structures in the computational graph. Most prominently, cycles or loops. So where you can find cycles and loops in the LLM workflows. Think about you have a multi-hop reasoning process, a COT style reasoning. You will get an answer, use this answer to input it itself, and get the answer again and use it again, and you are writing a cycle when you do this, right, in the computational graph. Or if you are working with a multi-agent system, you have agent A talking to agent B, and agent B provided feedback, and agent A was dealing with itself again, and its input from agent B is further dependent on the agent A. So you have another cycle. Or needless to say, if you are dealing with a multi-round, multi-party conversational bot, then everything you have are basically cycles. So this is a pretty important data structure, but not well addressed in previous work. Also, there are also we find those methods don't evolve well when the data comes in over the temporal way. Like in a chatbot, you want to involve the prompt as a 1 round conversation, 2 rounds of conversation, and I keep talking. You want the chatbot to be more intelligent. However, those methods are not optimized for that, and you can only do that on a per round basis. Specifically for DSPY, it has a great support for discrete search, but it's not designed as an auto-differentiate backbone. TextGrad has supported gradient-like optimization. Again, gradient-like optimization. But as we mentioned, only support relatively linear workflow and handles relatively simple applications. And one last thing, when we scale up those systems to optimize a really large multi-LM workflows, we find they tend to if you want update prompt, those algorithms tend to update every prompt you run into the flow. But if you have multiple parties, let's say in a conversation case, you have multiple parties joining the show, the outcome doesn't do well, but not necessarily everybody was a joy killer, right? There may be just one bad guy and you want to update that, so why update everybody else? So we want also, as we scale up, we also want to be more focused in debugging or improving, and that not only helps efficiency, but also helps the interpretability where it's wrong in a compound AI system. So with that, I'm finally able to talk about what I'm working on. So I have three aspects to share with you. First is our effort, how to further scale up what prompt optimization has already achieved into LLM workflow graph, and I will explain what that means. Second was a work we did to discuss the potential privacy leak when we do prompt optimization and how to mitigate that. Third, I will tell you how we use part 1 and part 2 altogether in a real user case. So let's start part 1. This is actually a paper I did with a side project with an eternal friend. So I probably shouldn't even affiliate with my university here. Should be an independent research. But I'm only interested in the research itself. But I want to mention that my friend Lee has pushed this really far away. So first, since we have this work, she first wrote a software package called AutoFlow, which have become pretty popular on GitHub, probably still top 5 in all the prompt optimization stuff. You're welcome to use it. And then she decided to commercialize this idea. And her company just received the pre-seed from some venture capital that you may be able to recognize, and some other investors. And her team is now doing pretty well. And I'm very happy to see a research idea is actually coming into a company, even I have 0% in this company. Okay, now let's look at LLM workflow that I tend to call complicated workflow compared to the simple linear structure things we just talked about. Let's see this graph. We have 3 types of components here. A LLM component, a functional component which do things such as retrieval, combine list, the subquery, and a loss component which will do evaluation. Here, let's say we have a prompt. We go to the LLM, query it once, and then activate RAG. And this RAG result with LLM will go into the same LLM again. And I'll do another RAG. And the first round RAG and the second round RAG result will be combined, consolidated using combine list function, and using this combined answer to query the LLM for the third time to further refine the result. And here, for the combined query, I may have another prompt to ask more specific things. And this final answer goes to a loss function and do evaluation. I hope now you see the difference, what I mean by a complicated workflow. So you have multiple branches in the workflow. You have cycles, and you have multiple prompts serving different purposes. And this can only scale up even more. In order to handle workflow like this, we implemented this LM called AUTOML25 package. Features 3 aspects. First, it natively supports arbitrary computational graph, including cyclic pipelines and the functional node that even doesn't support gradient. We have implemented auto differentiation over all of them, and it naturally supports optimizing those cycles. Second, we support cyclic and temporally involving optimization by introducing a feature called time sequential feedback. And third, we present selective debugging to not blaming everybody, but only blaming who is actually playing bad. I'll give you some more details in the next. First, how to handle LLM computational graph. 3 things. First, we do have this is a programming thing. We do use a graph-centric program instead of linear program. But anyway, so we just allow you to write cycles in the program code now. And similar to TextGrad, we allow you to use LLM as a backend engine to optimize and loss function. But anyway, that's a setup. What really matters here is, in order to handle the cycles, we have gone one step beyond using TextGrad's algorithm, which you could consider, I have been describing like backpropagation or stochastic gradient descent in workflow sense. We have gone one step beyond that and implemented another algorithm you should be familiar with called BPTT, back propagation through time. This is how you should see this. In text graph, they only care about step-by-step and linear structure. And when you propagate it back, essentially, you are using each step, the loss function, to supervise itself independently blockwise and chain them together. However, think about RNN optimization that we're more familiar with. What would do? You would do, well, this is like in RNN context, what a text graph would do is like doing teacher forcing without considering any sequential dependency. But what is more popular in RNN? You will unfold the recurrent computational graph, truncate it if needed, propagate the gradient back, and then do weight sharing to distribute the credit, right? BPTT algorithm. So we implement this in LLM AutoDiff. Basically, when people first specify the configuration, we will do a cycle detection and see if there are cycles in the computer graph. If we see a local part of the graph is a cycle, we will apply the BPTT optimizer, where we will also unfold it into a temporally sequenced workflow. For example, consider it's a multi-round conversation bot. We will unfold it back into third round conversation, to second round conversation, first round conversation, and then propagate gradient and then do gradient sharing across those rounds. So that's become the actual optimization of a recurrent structure. And for others, if there's no cycle, we'll just use a gradient descent like what TextGrad did. We also implemented another familiar feature on the workflow level called a pass-through gradient. Shouldn't be a stranger to people. If we work on functional node that are not LLM and cannot produce any text, that means we cannot generate the textual gradient, such as retrieval or formatters, combiners. We will just pass the gradient through them from its output and input. And so the entire workflow can still be optimized. Oh, I hope you see that we are really doing the common sense level things to fill in what TextGrad hasn't been doing, but those things matters in actual performance. That's the first page. Why we can where we enter to handle any computational graph. Second step, we realize there is something different while we're trying to borrow concept similarity from RNN. There is a difference. We find that in LLM, it matters to record when the gradient has been received and it's caused by what time edit. Different from what RNN optimization would do. You just take all the gradient and average and apply, right, from different round. And let me show you why. Basically, what we discovered is if the same LLM, for example, has been called multiple times, like in a multi-hog RAG or agent or reasoning, for each time it is being called, we will record a separate time-stamped textual gradient for each time. So we know that for the first time, each gradient was generated at which physical time, and they are ordered by time in the memory. And then the feedback, so we don't want the feedback from a later step to accidentally rewrite what an early step should do. And why this matters? Let me show you an example. So I got this prompt and question. The Yuri Gagarin is the first person into space, and Wang is the first person sampling on the moon. I hope you see that. I hope you see that I'm making a particularly tricky question because the first sentence is actually a distractor of the second sentence. Yuri Gagarin has nothing to do with the answer of the second, but yeah, that's a tricky case. Let's see what prompt revision would be distracted in this case. So I'm calling an agentic system, putting this prompt and a question. So the first thing we would do is to decompose this question by generating subqueries. We will ask our LLM to decompose this question into two, and for each of those questions, I will answer the first question, calling this LLM once to answer the first question, and calling the same LLM twice to answer the second question. The first and the second answers will be combined together, going to evaluator, and if it's wrong, we start to revise the gradient. In this case, LLM start to decompose the question into first, who is the first person stepping on the moon? And the second, what was he born? First question is fine, right? And by a web search, you can find that's Neil Armstrong. And for the second, what was he born? This becomes a very ambiguous question. Who is that he? And if LLM is doing this, it will look back in the context window. who is that he? And that is why I particularly place a distractor sentence here. When Yuri Gagarin, because this is perhaps a name, a first name, this LLM will see in the context window. So it's very easy to mislead this LLM to think I'm asking when Yuri Gagarin was born. And so that causes wrong solution. And now see what the prompt optimizer's behavior will look like if we do not record when which gradient, which question was asked first and which gradient should go first. Remember, we need to ask two questions and combine those two question answers by our LLM call and then go to evaluation. So if the loss start propagating, you could consider this layer to be like a pooling layer over temporal information. And after going back towards the pooling layer, I need to assign the credit or distribute the error into the two sub-questions. Up to this pooling layer, this loss was generating a feedback saying that you didn't answer that right because the resolved identity wasn't you should refer to the resolved identity instead of use the pronoun. The pronoun causes ambiguity. Fair enough, right? But from this step, who we should blame in the multiple sub-questions? If we do not label those questions by time, then there is no way for us to identify which question was causing this problem because they all look the same. They're like in the same batch. And this gradient purple back, it will give those two, give the prompt information that, okay, we may all committed this question, so this problem. So let's reflect all of us. And that will cause a totally unnecessary revision like this. As we say, so in all questions, because all questions this prompt asks us to use a resolved entity. So the LLMs tried hard. Let's not use alien pronoun at all. The revised prompt will now look like this. It's a real experiment, by the way. The first question is revised into, is Yuri the first one step in the moon? Because I want to avoid who or he is. But that's totally unnecessary, right? That's overkill. The second question was revised right, who was nail-bound, but the first question become a distractor by itself. So that caused a conflict case. And if you keep doing optimization like this in prompt, you will find the errors become oscillating and very hard to settle down. How to fix this? Simple. Instead of putting those two gradients both into memory, I would use a time index dictionary to support them. Order 1, question and answer, order 2, question and answer, and when gradient come back, they will be marked to which question they correspond to, and we know which question will ask earlier. That was the information we try to pass through the order. So now if we have an ordered question list, see how prompt optimizer will work here. The loss function come back, and because now we have specified which question come earlier, which question come later, this loss function is able to properly specify their temporal dependency and give feedback like, the first question is fine, but the subsequent question should use the resolved identity. This is the temporal resolution we want to preserve when you have multiple loss and multiple gradient back. And with this correct update, I know that I only need to touch the second prompt replace the name with output of the first prompt, Neil Armstrong, but the first prompt, nothing to touch, and this question is solved. So a simple tweak, but a pretty underappreciated observation from the previous prompt optimization work. Third stuff, sparse update. I just cannot resist doing that because sparsity is probably closest to my heart. But we have find two parts of sparsity pretty naturally embedded into this framework. First, we realize that in modern day prompt, like the 60-page one from cloud, they are not a big chunk of text. They are very structured with different aspects of things. Usually a good prompt, as I said, have problem definition, instruction, guide rail, output format, a few short examples. And we specifically ask our input to be formatted this way. And we will, instead of generating one gradient, to the whole trunk of prompt. We ask the textual gradient, the revision to the comments to be generated to each subpart of the prompt. Because that is because we find we find in long prompt, if you use the text gradient to optimize that, you have a cross contamination. You revise something to be right, you accidentally cause something to be wrong, and that called unstable optimization as well. The other sparsity is the other sparsity is in the batch samples. So the batch samples mean because we need to load human data, that we need to do the human provided demonstration to optimize this prompt, the training data. And in a batch of training data, we find because the LLM is a pretty intelligent guy, it will generate the prompt, even your initial prompt will be fine for many of those examples. So the loss will be 0 or nothing to revise. And that will cause the true errors to be diluted in gag propagation. So we decided to highlight those errors and especially high-stake error cases by only backpropagating using examples that are most error-prone or demonstrate very large errors. And we find this also help us scale up to really long prompt and complicated tasks. So those are some okay. So that's all we did. This overview is all we did in this LLM AutoDiff package. But all those things to me are pretty straightforward algorithm ideas, but they are easier said than coded, I'll say, and it eventually become a pretty sophisticated software package. We have benchmarked our result in a best effort way with two SOTA, DSPY and TextGrad. In all except one task, we have tried from basic task to task that frequently call functional tools and tool calling versus multi-node graph. Those are relatively simple things because I think by the time we roll the paper, we don't even have a chatbot benchmark that would allow us to optimize more than 5 rounds in evaluation. So we find that first, TextGrad is pretty competitive in basic task. But when the tasks start to involve functional calls and cycles, TextGrad become very unstable. And we call it a gradient explosion, again, reminding you of what will happen in recurrent neural network when cycles are introduced. And DSPY and both DSPY and LLM AutoDiff work stably because DSPY doesn't rely on gradient at all. It's a discrete search method. So it also extends to those. Pretty competitive method for both, but in 3 out of the 4 cases we look at here, LLM AutoDiff outperform DSPY, which is pretty happy for us because considering how much optimization has been in that package already. So we have later put more innovation in LLM AutoDiff by considering introducing the momentum variant of SGD. So due to the sake of time, I'm perhaps skipping this part. You are welcome to check our paper called Scaling and Textual Gradient on arXiv. The basic idea is instead of optimizing just one prompt, we allow you to keep a temporal trajectory of prompt along the optimization. And each time generating a prompt, you also take reference to the old prompt, essentially mapping the concept of a network momentum into this textual optimization process. And that helps us to scale up, to even longer prompt and make optimization converge faster and boost accuracy in general. The second part of my talk is is about prompt optimization with privacy. I'll probably go a bit faster on that part, sorry. So after we have studied the prompt optimization for a while, we want to look at how people are using that in the industry, especially in the highly proprietary areas. So for companies like medical or financial firms like the one I'm currently working for, we are all very secretive. And there is no way we're going to send the data up to the cloud API. But yes, of course, we can use DeepSeek and Chainone, but let's admit that the cloud APIs, the Grok, ChatGPT, and their peers are still the strongest ones, and sometimes we're lured to use them. So what are the trade-offs we can use? We can use it by protecting our data privacy. One pretty common way that I know some companies are already doing is called offsite prompt engineering. That works in the following way. Let's first get one of the good offsite local LLMs, Llama, Chainone, or whatsoever, put your local sensitive data in this LLM, because anyway, you host that, and use prompt optimization over your private data in your local server, get a good prompt, and then put this prompt into the public domain LLM. So you customize this public LLM GPT also to display the behavior. It's a kind of privacy-aware behavior steering of public LLMs. That sounds good, but if you take another look of what are the prompts being made, that would be more alarming. We did one experiment with Vikua in prompt optimization. And apparently we'll send Vikua mailing text materials, that's what we assume to hold locally. And we find the prompt generated by Vikua will include raw text from your private data. They just become part of the prompt in that big trunk that you probably never care to look at. And now you're comfortably throwing this long prompt to GPT again. So really you are fooling yourself, right? There is a apparent privacy leak. So we decided to do a bit here by introducing differential privacy the regime into offline prompt engineering. So the idea has been largely following a general function privatization. We use a mechanism called exponential mechanism and modify that to only include the top K generation as a token. So it works like the following way. Assume this is my private data. We will cut that into multiple pieces. And for each piece, I will use it to individually generate a prompt. And following some utility function, I will probabilistically mix the prompt generated by different disjoint subset of the training set. And because every token in the final output is a probabilistic mix of some prompt generated at a different data subset, it tended to limit the influence of any single data sample at any single location of the prompt. And we further add some noise in the prompt generation process. The good thing about that is by doing this, we're still able to keep good theoretical properties in differential privacy. And we're able to show that if you do in this way, you are guaranteed any sample you use to train this prompt wouldn't have more than certain threshold influence in the final prompt. And we find it to work pretty well as well. So in this table, for a text classification task, we have benchmarked what options we may have if we really want to do this thing, build a strong prompt from private data and then use a public model. If you don't care privacy at all and upload all the samples, to public model, you get 82.9. If you do care a little bit, but not too much of your data privacy, you do what I said in the very beginning. You will optimize this prompt using a local Vikua also, and using this prompt, whatever that contained, and throw that to the cloud. That gives you almost the comparable performance of directly sending the data up. In the good sense, you could say this prompting is powerful. In the bad sense, you really don't know what is being included in that prompt, but it works in the utility sense. So those are the two relatively privacy unaware way. Now, if you care about privacy, we have tried two baselines. Number one, don't use the private data at all. And this is the zero-shot result, which basically means don't tell GPT anything and let GPT work it out anyway. And you see the performance gap. You're losing 6% in this privatized domain task. And we also tried another baseline to use a differential private SGD to fine-tune a cloud model and match the performance. And we realized that training language model with a gradient contaminated with differential private noise is a very challenging practice. And the performance degraded a lot. Finally, if you use our solution, which use a local LLM to learn the prompt in a differential private way, you get a performance still close enough to the two privacy not so well solution and largely outperform the other solutions that don't use privacy information at all. So we see this as a good practice. Okay, we have 5 more minutes, and I want to show you an application of our algorithm in a joint project we have on the mental health care part. I really like this one. So the application we're looking at is dementia intervention for aging people. Interestingly, for this disease, people have find non-medical, non-intrusive intervention by just talking to patients or potential patients is greatly helpful because of many of those patients, if you look at their profiles, they are isolated senior people that don't have enough social interaction. And what LLM is best at? Talking, right? So we are not the first to build a chatbot and let LLM talking to the senior people. And we have good, and people have great motivation to do that. Because previously you need to hire people, train people, send them people at home that have cost concerns, availability concerns, and sometimes safety concerns. But by training a digital twin of LLM, you can talk 24 hours a day if you want, and the cost is just the electricity bill. So pretty attractive, but the effectiveness of generative AI talking wasn't super validated. I'm not sure if any of you really favors talking to GPT for an hour or so, and how appealed you are by that conversation. We work with doctors and see how we can do that better. We realize that for a good chatbot to work for this mental health care, you need two aspects. Number one, guide rail. That's what people will train the volunteers to be. You need to pay attention what you can say or what you cannot say. And for the volunteer training, we have converted a big talking principle handbook into prompt. Usually, what was the easiest way is just throw that handbook into prompt and tell the chatbot you have to follow this. And the second part is personalization, which is even more subtle, because different people has a different talking habitat. And an experienced volunteer should adapt his or her talking behavior, right, gradually to fit the patient's need. But a GPT won't know how to do that. And we have to design prompt to adapt, telling that you want to be more engaging. You want to ask more questions for this specific patient, etc., etc. Oh, previously we do experiment by manual prompting. And that very quickly, as you can imagine, proved to be inscalable. We started by working with 9 patients and then 15 patients, and then that already overwhelms us. Because prompting has, in order to have enough data to to tune the prompt, you have to first have a lot of conversations going on with AI and the patient. And those conversations will need to be curated into training data and then go back either manually or use prompt optimization to tune the prompt. The data scarcity is an issue, and the data quality is another issue. So we decided to automate this whole process. And we did three things. First, we trained a digital twins of our patient by letting our LLM being trained on patient's daily dialogue and try to let this LLM to talk like a patient or a potential patient. And this way that become our synthesized data generator. So we don't have to bother our patient to train our model. We talk to the synthesized data for the data synthesizer first. To other part, we decided to fully automate this prompt optimization process as individual patient adopt that. And this is backed by LLM AutoDiff in the back. We also want to respect the patient's privacy because the patient may often discover may discuss quite a private life experience to the chatbot. We want to use their conversation to optimize our chatbot, but we don't want to memorize any of the specific life experience. And how we do that? DPOPP. We have a privatized prompt optimizer to process them and make sure we don't memorize any of the actual dialogues. We just memorize them in the prompt in the format of prompt. So this become a really really good synergy. I like in a part of my research, because that really it doesn't happen a lot to me that two of my independent research converge into a third research project, and they actually work nicely together. Oh, we did a quantitative study with digital twin users, and it worked fabulously. I will skip numbers, but generally I want to mention that our fine-tuned LLM compared to GPT API by default are able to let the users talk more words, which shows a great deal of engagement. It lets the users recall the past memory more, which is a good sign because a clinical study has revealed if you can incentivize this a potential patient to recall more of his or her past life, this is a good practice to avoid cognitive decline. And that's highly encouraged in therapy. And we are able to achieve that in our conversation and let the patient talk more about past memory. And the patient also are incentivized to ask more questions back to the chatbot, which is another good sign we pursue. And now this is under a formal IRB-approved clinical trial with our partners at Massachusetts General Hospital. So this is a tiny slice of the prompt we have optimized from the medical data. Some example, and here I highlight a sentence. This is a sentence discovered by LLM AUTOML25 in one of the patient conversations. So in this specific patient, we have discovered that the patient does not practice a lot of the reflection of the past life. So we add LLM AUTOML25 automatically add this one sentence. This assistant must practice reflective listening more. And there we have more examples throughout the prompt design. Some of the example conversations, but I want to use the last part to show you our demo, actually. The patient here was played by my pool student. Sorry.
Hello. Hello. It's so nice to talk to you again.
So this.
How have you been feeling today?
I feel good.
Is it good? Output for once? Yeah.
That's wonderful to hear. Do you remember our last conversation? We talked about a few interesting topics.
I forget what we left off last time.
That's perfectly okay.
This guy is actually
Last
trying to
time we talked
mimic
about some everyday
how a
topics,
cognitive
shared
declined
stories.
patient may talk.
Today, we can
Talk
start
slowly,
fresh.
talk in broken
If we have
English,
to discuss,
and being
we can talk about politeness,
remarkably
conflict
resistant to
resolution,
continue the
or
conversation.
forgiveness.
And we
If
are
it's hard
doing
to
stress
choose,
testing how this chatbot will do.
what do you think?
Sounds good. Let's go ahead.
So the chatbot will start by talking about sympathetic or memory calling topics and get an easy start of the
Great
conversation.
choice. Forgiveness is a powerful and important topic. All about letting go of grudges and freeing ourselves from past pain. Can you recall a time when you had to forgive someone?
This is the
How
desired
did it make you
behavior,
feel?
recalling past memory.
Yeah, I have a story back in a little town.
That's good to hear. Forgiving someone can often bring a sense of relief and peace. Do you remember what helped you decide to forgive that person?
So prompting more of the memory.
Oh, well, it's a story in a little town long, long ago.
I understand, and there's no rush. If you'd like to share even just a bit about it, I'm here to listen.
Those are
If
all
it's too
from
much for
all
right
the
now, that's also
guidelines. You want to
perfectly
activate the
okay.
interval if the patients seem to stop talking.
Thank you. One evening, my granddaughter Lily came to visit me, and Simon decided to share some story.
And stopped again.
You're welcome. My name is Lisa, and I'm glad to hear your granddaughter visited you. It's wonderful that Simon decided to share a story with you too.
Okay, for
Family
the
and
time of
friends
sake, I
sharing
will probably
stories.
stop here. But I hope those pieces are showing the behaviors we want this LM to behave. It's become a more sympathetic, emotional, sensational helper to the senior agent. So that basically concludes my talk. So for the last page, I just want to highlight two of the main contributors to work I talk about today. One is my friend Lee, who is already starting a company, and she's recruiting people. The other, oh yeah, this guy, that poor guy was just talking to the chatbot, who was unfortunately my postdoc and joined National University of Singapore as assistant professor, and he want a PhD student too. That both of them insist I add this page. Thank you.